All right, it's 7:01, so we will get started at this point. I will give a short introduction at the beginning, and then we'll hand it over to you, Bruce, for the presentation. So good evening, good morning, afternoon, everyone, wherever you are located in the world. My name is Mehdi Mortazavi. I am the University Outreach Committee Chair for the AIAA North England section. Before getting started with the Zoom presentation tonight, just want to take a couple of minutes to introduce myself and also some of the activities and opportunities that we're offering in the AIAA North England section. So we do have programs, providing $250 grant for K-12 STEM teachers and administrators. Our section is also joining sections in California and Florida in the AIAA Partner Aerospace Robotics Competition, which is partially funded by the Gates Foundation. We have purchased 10 Tello mini drones for potential high school teams. Our secretary, Hiro Endo, is flying one of them with the Drone Block app. We're looking for college students and professional mentors for this effort. We've also begun our diversity, equity, and inclusion effort with an outreach to a group of National Society of Black Engineers Aerospace last Saturday. We are hoping to have a liaison to our council from them. We're also striving to make our sections more diverse. We have liaisons from other groups, including the Women of Aero Astro and the Vertical Flight Society. We're planning for our monthly Zooms to the section, which is underway. Any suggestions are appreciated. We're posting presentations and studies to the AIAA North England website on climate change. The ODC is observing system for measurement of climate change, which has participation from 11 colleges and universities. Also topics on sustainable aviation and advanced fuel system. As always, please feel free to contact us with any questions, suggestions, or offers to participate in the section activities. With that, that concludes the introduction on the AIAA North England activities. And so I will move on to the presentation. So tonight's Zoom webinar is titled Hydrogen for Aviation by Dr. Bruce Holmes. Giving a little bit of a background, Bruce is a 5-decade veteran of aviation operations, research and development, aircraft development, and disruptive innovation in his field. His background includes industry and government roles in research, operations, and executive leadership, working at NASA in the commercial on-demand air carrier world with aviation software startups on the US NextGen founding team, and most recently on an electric vertical takeoff and landing, also known as eVTOL air vehicle. In addition to his role as CTO for Alaka'i Technologies, launching the first hydrogen fuel cell powered electric air mobility vehicle, he's a senior advisor to SmartSky Networks, supporting the launch of a unique 4G LTE aviation connectivity solution and apps development platforms, contributing to the Internet of Things that fly. He serves on special groups for the National Academy of Science, Engineering and Medicine, the FAA Administrators Research, Engineering and Development Advisory Committee, NAS Operations Subcommittee, as well as an corporate board. He has published over 100 technical papers, received 7 patents in aeronautics, been honored with numerous NASA medals and professional society awards, including the FAA Wright Brothers Master's Pilot Award, recognizing 50 years of safe flying. He's a fellow of the AIAA and the Royal Aeronautical Establishment. He's also an active pilot and thrill owner of an Icon A5 amphibian aircraft. With that being said, I will hand this over to Bruce Holmes.
Mehdi, thank you for the introduction as well as for the invitation to make this presentation tonight. My hope is that you will find the information I'll share here interesting at the very least, maybe inspiring about your own careers if you're in the student domain or if you're in the in any part of the engineering food chain. You might see some information here that causes you to pause and wonder a little bit about what the art of the possible might be. Let me start with oil. Oil has literally and figuratively fueled our 21st century presence today, from cars to wars to economics and even geopolitics. You might say that we live in a culture of oil. Culture change must be one of the hardest undertakings there is for societies. Oil, fossil fuels in general, shapes nations through its geographic concentrations predominantly. Hydrogen has the very real potential to reshape that landscape in ways that help with geographic diversity and distributed production and consumption capabilities in ways that oil is challenged to do. The changes that this hydrogen economy, as we hear it called, might bring forth in nations are bound to be profound. When nations balance their books, for example, through sovereign funds using oil, and today are faced with the truly disruptive nature, perhaps, of a hydrogen economy of tomorrow, they will need to adopt very different ways of governing. They will need to tax their citizens, for example, and this will not happen easily without becoming more representative than many are today in governance. Remember, no taxation without representation, for example. Oil today is the DNA of our culture in society and our governance structures. Well, will it change? Can it change? I believe that just like every other disruptive innovation, sort of borrowing from Harvard's Clayton Christensen book of the past, The Innovator's Dilemma, the answer is, in my mind, without a doubt. The path will be hard to predict in timing and in direction, but the change will be driven, like other disruptive innovations, through more performance with less cost, along with scalability in ways that hydrogen can and oil cannot serve. Think of the difference between oil rigs in the gulfs of our oceans and hydrogen production, even in your backyard one day, perhaps. There are other less challenging drivers, in my opinion, like public opinion, oil lobbies, of course, although all of that's changing. Well, how might aviation benefit from this evolution? And when and what might it look like? Let me introduce you to some of the experiences that I've been having in this world. I'd like to share with you a technical view. Why hydrogen, why liquid hydrogen for aviation, and what the vehicle design implications might be. I'd like to share an infrastructure view. How might we achieve H2 at scale? And could we start with H2 at airports, for example, or heliports, vertiports, and the like? And then a sustainability view about the ability in hydrogen fuel cell stack systems to be recycled and reused in ways that are rather difficult with other power plant systems. And then introduce the notion of brown, gray, blue, and green hydrogen as it's beginning to unfold in mostly other parts of the world, not so much in the US yet. But if I had to make a prediction, which is always a scary thing to do if it's about the future, I think the coming few years in the United States, we'll see a hydrogen initiative, a set of initiatives grow. Just a bit about Sky, our air vehicle. Just so you know, the experience that I'm basing a lot of my commentary on is the development of this vehicle over the past few years. In Stowe, Vermont, we have a prototype engineering and flight test center at a little airport out there called Minuteman, 6 Bravo 6, for those of you who track airports by ICAO codes. And the vehicle is a multi-copter. It's a hexcopter. It's fueled by a liquid hydrogen tank and 6 electric motors, of course. Fairly simple in the sense that they're fixed pitch rotors, and the vehicle employs the latest technology as anyone would expect in terms of multi-redundant paths for flight control systems, for hydrogen powertrain fuel cell systems, including the ability to fly autonomously, but not as a commercial implementation at first. The air vehicle will be piloted. It has 5 seats in it, 1 for a pilot, 4 for passengers, and a very convertible form of interior configuration for other missions as well. A little bit about the overall competitive picture for hydrogen and the liquid hydrogen advantage. If you look just simply at power density for hydrogen and for batteries, for example, and for a hybrid power system, the prospects for advancement in all of these energy carriers for aviation applications give an edge to hydrogen from a purely vehicle capability standpoint. There are other factors that have to be thought of course, which include certification, the whole business of infrastructure for hydrogen energy sourcing, and the codes and standards related to the management, safe management of hydrogen in aviation operations as well. A bottom line about this is that while hydrogen may have certain advantages in power density over the battery electric solutions for powertrains, both of them have places in this world, and they have benefits, and many of those benefits depend on how much endurance you really need and how much payload you really need for the mission profiles you're trying to satisfy. So it's great to see the battery solutions out there. If for no other reason, then it's been a tremendous source of innovation in propulsion, aerodynamic airframe integration analyses. So let me give you just a bit of a bottom line about the implementation of a powertrain based on liquid hydrogen, HFC, or hydrogen fuel cell technology. This is a bit of a history chart in one quick look, if you will, with the air vehicles across the bottom axis. You can see in the left-hand bracket the fixed wing from large to small, starting with the Airbus A380 at the far left, and then moving all the way down to aircraft like the Piaggio P180 on the right in that first bracket. And then in the second bracket across the bottom, the light to heavy rotor wing aircraft, starting on the left again with the things like the Bell 206 or the MD 500, and then moving over to the right to the larger ones that include things like the Sikorsky S92, for example, and others. And then you see just a couple of sampled battery eVTOLs on the far right bracket on the bottom axis. And then in the colors, you see the red operating empty weight as a percent fraction of gross weight. It's just simply a way of expressing, a mass fraction of the structure of the vehicle. And you can sort of see these straight lines drawn through the fixed wing air vehicles. As they get smaller, the mass fraction of the air vehicle structure grows relative to the gross weight. Not too surprising. There's efficiency and scale in aircraft design, and there you're seeing it for that parameter. And then if you move to the right on the red line, you see another straight line through the next phase of rotorcraft, and a very similar pattern of behavior where in this case, it's interesting. It's a little bit different in the sense that the increasing for rotorcraft, the increasing size of the rotorcraft actually reduces the operating empty weight efficiency. Kind of an interesting development. And then you also see in the blue line the payload mass fraction for the vehicles going from left to right, from fixed wing to light rotor wing and then battery. And you can also see that operating empty weight fraction of gross weight for battery eVTOLs is declining. And what you see also is that for a liquid hydrogen, the three dots, the red, the blue, and the green dot, that the mass fractions for a hydrogen fuel cell powertrain solution are competitive in the space of the other vehicles that you see in this comprehensive graphic, which is interesting all by itself, because when we started our journey toward our hydrogen powertrain solution, we weren't quite sure that this was going to be possible, but it's turning out to be not only possible, but beneficial. A little bit about the infrastructure. This is the major challenge, well, one of the major challenges that those of us in the hydrogen space face. And if there's some good news here, it's the fact that the world is taking on hydrogen. You might call this the third life of the hydrogen wave, or the third wave of hydrogen enterprise development over history. And in our case, with the idea for air vehicles, what we're contemplating and what we shared at a recent Department of Energy H2 at Airports workshop, which was hosted both by DOE and by the FAA and the Air Force, that we see an opportunity to provide what you might call vehicle agnostic energy stations that could begin with green sources of electricity for inputs to the electrolyzers that then produce out of water hydrogen, and then for the liquid hydrogen users, of course, a liquefaction machine that would produce the liquid, and you'd want to do that pretty much on demand because it's harder to store than gaseous. But you can also use this hydrogen to recreate electricity for battery charging, for example, for cars or other electric vehicles and trucks, and then for hydrogen-powered air vehicles or hydrogen-powered cars use these refueling stations in kind of an ecumenical, let me use that word, sort of way. So it's a bit of our vision about how to move forward in a fashion where aviation can be an application which can help make the stronger case for hydrogen globally. A few words about sustainability. Why batteries? And then, of course, why hydrogen? I think what is fairly easy to understand about the focus of the past, let's say, decade or so on battery electric solutions for powertrains for aviation is that they're plentiful, they're available, they're reasonably affordable as a initial expense, at least, and they are flexible and have opened the door forevermore through distributed electric propulsion for changing the aircraft design envelope. That design envelope is forever changed as a consequence of the work of the battery electric consumers and distributed electric propulsion. Once you can distribute electric propulsion anywhere, sort of, that you want on an air vehicle configuration, that means you can now change the configuration to satisfy demands such as vertical takeoff and landing in ways that were simply not practical, either through acoustic, noise-related issues or powertrain mass fraction-related issues, and others as well. And then on the hydrogen side, what hydrogen offers is the ability to have the cleanest end-to-end solution for powertrain development for any application, including aviation. A little bit more on that point I made earlier about the evolution of aircraft configurations. Think for a moment about how long it took us to migrate from, biplanes to monoplanes, from strut brace to cantilever lifting surfaces, from engines on tails to just a fairly common configuration of engines under the wings, and ultimately from configurations of the past to the wing, body, tail, tubular thing that we take for granted in single aisle and multi-aisle air transportation aircraft. And then consider, as I said earlier, the door that has been opened wide for creative thinking about neo-electric solutions that are now possible by virtue of the advancements not only in batteries, but also now in hydrogen powertrain, fuel cell stack system efficiencies, as well as the related motor technologies that have come along. When you see companies like Rolls-Royce making decisions to move into the electric motor space, for example, there's a signal there. When Cummins, the world's largest and probably one of the oldest diesel powertrain manufacturers in the world, decided to buy Hydrogenics, who are our fuel cell stack one of our fuel cell stack manufacturers. There's a signal there. It's that people are beginning to see the future. A bit about hydrogen itself and its production options. You can make hydrogen in a lot of different ways. I'll tell you a little story about my own experience when I was probably about 12 years old, growing up in the suburbs of Chicago, and my buddy and I had studied my chemistry kit book about how to make hydrogen. So we pedaled our bikes down to the Bartlett hardware store, Bartlett, Illinois, and bought a gallon of sulfuric acid. Pedaled the bikes home, went down the basement, cut up my mother's zinc bottle caps that she used to make, canned, jarred fruits and vegetables, for over the winter and things like that. I'm not sure I remember distinctly getting into trouble about that, but I probably did. But anyway, we dropped the, slivers of zinc into the hydrochloric acid bottle, put a balloon on top, and lo and behold, we created lift. All right, we tied it off and took it outside, let it go and fly in the sky. It was a mesmerizing moment for me, and little did I imagine that all these years later, I'd be wishing I had stayed more awake in my chemistry classes in freshman college, both times. But there are many ways you can make hydrogen. Black hydrogen is referred as a reference to steam reforming of coal-based feedstocks. And it really is quite as simple as making steam and then literally blowing the steam through coal feedstock materials that then cause the reaction that separates the carbon and the oxygen and the hydrogen in order to create separated hydrogen. Gray hydrogen is referred to as steam reforming of natural gas feedstock, a little bit less of a carbon footprint in that case. And then blue hydrogen we refer to as reforming of natural gas and capturing CO2 and storing it and reusing it for other things, including, which I just came across an article today in IEEE magazine about a group that has figured out how to use liquefied carbon dioxide, combining it with water and splitting the water into hydrogen, oxygen, and then combining the hydrogen with carbon dioxide in a reactor and making vodka. Apparently it's pretty good. They charge $70 a bottle for this stuff. So anyway, there are other uses, many uses, of course, of carbon dioxide. So that's blue hydrogen. Green hydrogen, of course, would be produced through electrolysis from renewable electricity, which can include, of course, photovoltaics and solar form, as well as wind turbine. And of course, if those of you who live on the East Coast of the United States and probably coasts of other countries are seeing the proliferation of wind turbines for producing electricity, and the ability to use that form of green energy, green electricity for making green hydrogen is very powerful. Even nuclear can be a very valuable source of the electricity for producing hydrogen as well. A little bit about the life cycle of hydrogen fuel cell systems and their implications ultimately to operating costs over the life cycle of the vehicle itself. Of course, as I think many of you will already know, the fuel cell system basically consists of these plates that have it's almost a Gore-Tex-like fabric on them, along with some other materials, including a catalyst, which can be, for example, a very, very tiny amount of platinum distributed across that fabric frame. And then you stack these frames together. It's why we call them fuel cell stacks. One frame gives you about 1 volt. So we have a 270 volt system. So we have about 270 of these very thin plates stacked together. And that system then is the box through which you push oxygen and hydrogen, oxygen from the ambient atmosphere, of course. And you get electricity out of it. You also get heat, which can be very valuable in a reuse fashion for a couple of reasons. Not only cabin HVAC functions, but also energy feedback into the entire process for efficiency improvements in the fuel cell stack performance. And water vapor mostly as well. And so the value in terms of the afterlife of the fuel cell stack system is that you can recycle, rebuild, and reuse about 99% of the content of the fuel cell when its life is done. This is a very valuable part of the story for us, as thinking about how to make the most out of a hydrogen powertrain solution, not only for the vehicle capabilities, but for the effects on the planet. When we are thinking about the operating expenses for any air vehicle, we have what we sometimes refer to as a maintenance reserve, which is meant to pay for redoing the engines. In a piston airplane, you might have about 2,000 hours between overhaul. For the engine in a turbine engine, you might have maybe 5,000 hours. Well, one of the beauties about the fuel cell life cycle is that it's somewhere north of 10,000 hours. And we even have some of our suppliers making claims that they believe they can reach 20,000 hours between recycling of the fuel cell stack systems. You add that to the fact that the motors themselves also have between 10 and 20,000 hours of durability, and just enormous levels of reliability compared to any powertrain solutions we've ever had in aviation. These not only affect the future total cost of operations for these vehicles, but they also affect the safety. One of the certainly for smaller aircraft today, one of the remaining challenges in aviation safety is the failure modes of powertrains in those aircraft. A little bit about abundances and scarcities and the nature of losses in systems and what it means to the ways that I'm suggesting we and the engineering community need to think about hydrogen as a matter of abundance, not scarcity. When you look at the epochs that society has moved through, I'm thinking in the big frame of epochal changes from the Bronze Age, the Iron Age, the Agricultural Age, the Industrial, et cetera, et cetera. Think about with me for a moment the way in which the previous epic scarcity became an abundance, right? And so what was scarce became abundant, and it changed the nature of society. And I'll just take one example that's pretty easy to think about. In the industrial age, what was scarce and what was abundant? I suggest the simple answer is what was scarce in the agricultural age was power. What was abundant was land. And so as we moved across the threshold from the industrial age into the, from the agricultural age into the industrial age, that abundance of power became the propelling force behind the growth in the industrial age. And of course, along the way, we also had the oil and the petroleum revolution, and they went together very nicely to cause a convergence, if you will, of the abundance of power to the point at which you can think about something that we don't like to usually as engineers think about, which is we can waste power to solve problems of human need. And we do that today. We waste power. Piston engines are about 30% efficient, 70% waste, just as an example. But they satisfy human needs. And so I'm suggesting that as we move from an oil age to a hydrogen age, where hydrogen might have been scarce before, but because it is the most abundant element in the cosmos, if we can harness the means by which we convert it in its raw form into its useful form, it can become an abundance. And so as a scarcity becomes an abundancy, we should think about consuming, even wasting if necessary, that which is in abundance to solve human needs. Well, what this says to me is that when I look at the losses in any system, like thinking about creating hydrogen and then liquid hydrogen, and then transporting it, storing it, and using it, even after the losses of production, transport, and storage and liquefaction for hydrogen, we have losses from rotor blades, fuel cell support equipment, cooling systems, downwash from the rotors, the aerodynamics of the vehicle, viscid and inviscid losses, and gearing losses as well, predominantly those. And in spite of all those, we still come out, as I showed you in one of the earlier charts, with a operating empty weight mass fraction for the vehicle, which is respectable in the big scheme of vehicle design over the years. The technology readiness level for hydrogen powertrain systems is somewhere, I'm going to say, well, let me back up one step and say that for terrestrial applications in cars, buses, trains, forklifts, they're all at TRL 9. I am learning new things every day about hydrogen. I did not know until recently there are 4,000 cell phone towers in the United States whose former diesel backup power supplies have been replaced with hydrogen fuel cell power supplies because of the efficiency and the sustainability of hydrogen rather than diesel. There are 40,000 forklifts that are powered by hydrogen just in this country alone. And so if you've got a Walmart distribution center or an Amazon distribution center or anyone of those anywhere near you, and if you can, you should organize a site visit, road trip, whatever you call it, to go see and talk to the people who operate those systems and learn, boots on the ground, so to speak, why they're there and how they benefit the operations of those centers. So the terrestrial applications are quite mature in hydrogen fuel cell stack technologies. However, for aeronautical applications, that is not true. the TRL level is somewhere in the neighborhood of 4, maybe 5. And what that means is that, and this is very important, technology readiness level is a scale that was developed back in the late 90s, early 2000s, and used in spaceflight programs and many other aviation, aerospace programs. Many of you will be very familiar with TRL levels. And what they allow you to do on the horizontal axis, you see TRL levels 1 through 9. And then you see on the vertical axis cost as a percent, 100% meaning, the end predicted cost. And then the ability to become more accurate in predicting end cost of a new product as you increase the TRL levels is what this graphic shows you. Basically, what it means is that TRL 4 or 5, predicting most likely cost today is somewhere around plus and minus 30%, mostly plus. We just don't know. And it also means that the timeline for maturing TRL levels is also less known today than it needs to be to make commercial decisions. My point also here, and I shared this information at our recent workshop I mentioned with the DOE on H2 at airports, because the DOE is looking for ways to help promote and advocate and advance and accelerate the growth of hydrogen solutions. There's a long list on the right-hand side you'll see for hydrogen fuel cell systems R&D needs. One at the bottom of the list, which I'm a big fan of, is thinking about hybrid powertrain architectures. What could they look like? How would a combination of battery, electric, and hydrogen powertrain architectures benefit different emission requirements for air vehicle design, for example, and a long list of others as well. What we need in this industry are aeronautical industry pre-competitive collaborations, preferably hosted by the government, but led by government industry partnerships that are able to accelerate the pace and reduce the costs and share the risks of TRL advancements for hydrogen systems. It's fair to say that I said earlier, this might be the third wave of hydrogen over the past many decades, that we're seeing the movements by nations to declare themselves to become homes for hydrogen economies over the coming years. And of course, the primary drivers are environmental sustainability and total cost of ownership as well. If you ask yourself, why hydrogen, there are really 3 reasons if you think about it from a global standpoint. One is air quality. Another is energy independence and what I would call geographic equity through distributed production and consumption capabilities with hydrogen. And the third is the affordability of renewable supply of distributed hydrogen production. For aviation, there are 4 very much important additional motivations about why hydrogen. One is endurance. You get much more endurance with hydrogen for certain missions, especially heavier missions, let's say more than 1,000 or 2,000 pounds of payload, and more than an hour or 2 of endurance. You get more endurance, you get more payload, you get more fleet duty cycle. Duty cycles more than 80%. I'm thinking of duty cycle here as the revenue hours of an operation of an air vehicle or fleet versus the non-revenue hours that are a consequence of, for example, recharging or refueling times. And so fleet duty cycles for hydrogen vehicles will be up north of 80%, where they'll be much smaller for battery solutions for a while. And it just simply means you'll need more battery vehicles than you would hydrogen vehicles for the same mission profile for a fleet design, for example. And then the fourth one is lower maintenance reserves. And we talked about that a little bit earlier as a means of reducing ultimately the total cost of ownership. It's interesting to see what's happening also in the as this future for hydrogen begins to gain traction and unfold, the cost to produce hydrogen fuel cells has fallen 65% since 2010. And it's predicted to fall another 50% in the next 5 years, which brings the cost down from what was in the neighborhood of $1,000 a kilowatt a few years ago for stacks, which would mean $100,000 per car, toward the DOE goal of $30 per kilowatt in coming years, which brings it into competitive zone with today's internal combustion engines in cost. Other movements are interesting as well as evidence of what you might call leading indicators and signals in the market about the hydrogen story. Microsoft, for example, pledged recently to become carbon negative by 2030, in part by using hydrogen fuel cell stacks to power their Azure data center servers in a cost competitive replacement for their diesel fuel powered generators, with H2 delivered by hydrogen powered long haul truck vehicles to ensure 5 nines of total system reliability, for example. I mentioned that there were, almost 4,000 cell phone towers and 40,000 forklifts in the U.S. that use fuel cells, for example. And the volume of that production is what leads us to believe that we don't have to create our own volume in aviation. We can gain the economies of scale from other consumers of hydrogen and hydrogen fuel cells. And finally, the hydrogen production costs are forecast to decline by about 50% by 2030, and making hydrogen cost competitive with some conventional fuels. And that's before the impact of any technological breakthroughs are considered, where the total cost of ownership study's been done also by DOE. It is forecast to decline by about 45% at merely 600,000 vehicles per year. And they're mostly focused in their studies on terrestrial vehicles, but they do include the application potentially of aerial vehicles as well. Well, there's information you can go to and study on your own in terms of the trade-offs and the benefits and the technology readiness levels and the challenges in infrastructure, and the business of making hydrogen work in an aeronautical application set that applies the benefits of this unique and most abundant element in the cosmos, hydrogen. I want to thank you again, Nettie, for inviting this presentation, and look forward to any questions that the audience may have for a bit here.
Thank you so much, Bruce. Very exciting presentation. Very enjoyed it. And yes, we do have received a number of questions. We'll try to answer as best as we can in the order received. So without further ado, I'll get started with the question. I think one of the questions that are actually repeated asking is, how do you safely store the hydrogen on board? And how is the low temperature requirement maintained? Are there any potential risks involved in this?
Oh, yes. So hydrogen is neither more nor less safe than the fuels we use in our cars and trucks and homes. It's different. And of course, temperature of liquid hydrogen in particular certainly adds to that difference. The liquid hydrogen that we use is stored, at very, very cold temperatures. The storage tank itself is an insulated tank. There's a vacuum between the storage tank and the exterior of the tank. So, we carry about a 400-liter liquid hydrogen tank in the air vehicle, and then we use a hydrogen warming system to bring it up to the ambient temperatures needed to feed the fuel cell stack. that system and the codes and standards for the entire chain of activities that has to go from, let's start with a hydrogen storage facility on our landing pad, at the airport where we work, and then have a fueling nozzle that attaches to the vehicle, and then the vehicle stores the hydrogen. We're in the middle of our FAA type certification activity to satisfy them through the certification basis and means of compliance to demonstrate that all of that is safe. Much of that has been worked out already for terrestrial applications, and we're applying as much of that knowledge and experience as possible to our uses. There are hydrogen safety courses that Sandia offers, for example. I encourage anybody who even wants to think about studying hydrogen in design of vehicles to take that safety course. It's a very valuable course. It will show you what the risks are and what they aren't, as well as how the risks are mitigated and managed. And so all of our employees are required, of course, to take those courses. But one of on the plus side, there are some advantages to hydrogen in general. One is that when it escapes, and certainly in gaseous form, it escapes upward at about 45 miles an hour, in contrast to liquid petroleum fuels, which when they escape down on the ground and form a fuel air mixture in a fairly wide area, in contrast to a hydrogen escape, there's a safety difference there, but it's just part of the story. I mean, you still have to be very careful because hydrogen, of course, either in gaseous or liquid form, is going to be under some pressure. And so the tanks themselves have to be pressure capable and qualified for that. We store gaseous hydrogen at about 700 bar. That's a lot of pressure. And as you can imagine, because of that pressure, gaseous hydrogen tank is pretty heavy. One of the reasons we use liquid is because we're only at about 7 bar, about the same amount of pressure as in a champagne bottle, for example. And so it's a much lighter tank, and therefore very much smaller tank as well. And it's one of the reasons why liquid makes the most sense for aviation applications. But the record, the safety record for hydrogen to date is quite good. I don't have the numbers to quote for you about hydrogen incidents versus fuel, petroleum fuel incidents, or about lithium-ion battery incidents, which are part of the picture that we're all interested in managing safety about as well. But those are some considerations that we keep in mind. And of course, in the end, all of what we do in certifying our aircraft has to pass muster with the FAA certification standards that we have worked with them to develop. I hope that helps a little bit. I'd be glad to talk about it more if needed.
Thank you, Bruce, for this comprehensive answer. Another question we've received from a number of attendees is, how does the power to weight ratio of a fuel cell, stack compared to that of a gas turbine engine? Can we get the power density of an H2 fuel cell high enough to be competitive with a turbine using a generator?
Yeah, it's hard. Let me put it that way. Today, the power to weight ratio for our fuel cells probably in the neighborhood of 1.5 or so kilowatts per kilogram. And of course, what you have to consider is that you have to draw a system boundary around the whole powertrain system. You have to consider that the fuel for the turbine engine is going to weigh somewhere in the neighborhood of 6 pounds per gallon, right? And so if you have 100 gallons of fuel, at 6 pounds per gallon, you have about 600 pounds of fuel. Our 100 gallons or 400 liters or roughly weighs 60 pounds. liquid hydrogen. I mean, this is how what a fabulous energy density, energy carrier liquid hydrogen in our case is. And so the ability to produce a powertrain, and I should admit up front that a lot of that information is not the sort of thing many aerospace companies share in much detail, and so I'm going to be a little vague about it. But I will say that when you do your own studies and gather information from suppliers about the powertrain or the hydrogen fuel cell stack efficiencies, mass fraction included, take a look not only at what's happening today, but take a look at where they're headed with advancements that are already making progress, not only in the mass fraction of the powertrain efficiency or the hydrogen fuel cell stack efficiency from a kilowatts per kilogram standpoint, but also the fuel tank mass fraction efficiency. Liquid hydrogen tanks, the tank is about 2 to 4 times the weight of the fuel, the hydrogen in it, for example. And so that's the part of the math that you have to include in your analysis in the end. The rest of the story is that as the hydrogen fuel cell industry has been making progress, there's some interesting developments, lower TRL level for what we call high temperature PEM, polymeric exchange membrane, proton exchange membrane, sometimes called high temperature PEM systems that are moving out of the laboratory into applications that have a much higher power density than the current generation of fuel cell stack systems that we're using in our initial versions of our vehicle, that are largely derived from what the companies have built for terrestrial applications. Where in the past they really, for terrestrial applications in a forklift, for goodness sake, you don't care about lightweight, you care about heavyweight. You actually want some weight to keep the forklift wheels on the ground. And so that's been the case for a long time in the HFC world. So, those are all factors to keep in mind when you study what's happening in the fuel cell stack world. We're far from over, or far from completely mature in the way in which fuel cell stack performance is going to improve.
Great, thank you, Bruce. We have received quite a lot of questions. We still have time, so we'll try to answer as much as we can. I think next question is, what kind of certification requirements, whether FAA or EASA, do you need to meet for Sky?
Yeah, great question. We're categorized in the multi-copter aircraft category with a part. If you're familiar with the certification parts, we're in part 21.17 Bravo, 2117B, where we have an option that we've taken to assemble certification cert basis, we call it certification basis requirements, from various parts of the FARs. From part 23, for example, when the FAA rewrote part 23 in what's called Amendment 64 now, it was a major, excuse me. Stand by.
Bruce, I think you're on mute. You're still on mute. Let's see. There should be a button at the lower left. If you click on it, you should be able to unmute yourself. You're still on mute, Bruce. Bruce, you are on mute. Okay, now we can hear you. Yes, thank you.
Yeah, I said I couldn't unmute myself. That was confusing. Tell me the question again.
Next question was related to Sky. I think one person was asking for designing the LH2 system for Sky, did you take contrail formation into consideration?
Well, let me back up first of all to the certification question, and then I'll ask for some clarity about what's meant by contrary information. I think I know, but I don't want to assume anything. But on certification, we were able to assemble the certification requirements from all the relevant parts of the airworthiness regulations. Part 23 and the Amendment 64 rewrite is it's a very significant change from prescriptive standards to industry consensus standards. And so now the industry can bring forth, for FAA approval, of course, the certification standards and the means of compliance, which all of the industry players now are doing. And so that's allowed us to assemble an appropriate assembly of, if you will, of regulatory satisfaction requirements that are relevant to a vehicle that's never been certified, a vehicle type that's never been certified before for carrying humans. And so the FAA has been extraordinarily helpful in working with us and all the industry in moving these ideas forward. So we're very pleased with that certification process. The FAA and EASA are working to harmonize as much as they can. There are some very big differences between the FAA and EASA on certain requirements that are going to be challenging to ultimately settle into means by which companies that build vehicles in one part of the world can sell them in another part of the world. So we've got a ways to go, but progress is being made. Both sides, EASA and FAA, want to solve the problems that they're facing and challenges that they're facing toward harmonizing those requirements. There are a lot of issues in certification, not just in the aircraft, but we're also required and are working with the FAA along with our trade associations, industry trade associations, to develop how do you train pilots and certify pilots for flying these machines? Because I just pick a simple example. This aircraft does not auto-rotate. Right? That's why we have a whole aircraft recovery parachute system, for example. And where helicopters, traditional helicopters, rotary wing aircraft do auto-rotate in the event of a failure. Of course, we have got quadruple redundant powertrain channels, and so that's part of the mitigation as well. Anyway, I could talk about that a long time, but on to the design question about contrary results or contrary conditions or considerations in the design of the vehicle. We started with a battery electric solution, and we couldn't make it work. And so if that's probably the seminal contrary requirement that we were trying to satisfy, the reason we couldn't make it work is that if we wanted to add endurance and payload, we had to add more batteries, and it was diminishing returns. So the curve went like this. And when we discovered the hydrogen fuel cell stack solution path, the curve goes like this, where you add, if you want to add hydrogen fuel cell stacks, yes, you add weight, but in the process you gain in a net fashion endurance and payload. So it was a big eye opener for us. We are open, down the road to thinking about, how would, hybrid battery electric hydrogen powertrain systems benefit mission solution requirements and things like that, very certainly. As I said, also, we have considered and are implementing triple redundant fly-by-wire flight control systems and flight management systems for the 7 or 8 or 9 nines of reliability that we're going to require in order to certify these aircraft in both the U.S. as well as in Europe, for example. And we debated, of course, along the way about how many nines of reliability we need. The FAA's been deep in that conversation with us. We're pretty happy with the resolution, both from a cost standpoint and a total system reliability standpoint. So we've been looking at all that. We've been looking at alternative material systems. We're using composite materials, of course. The question is, are there roles for metals to play in our system? Just for example, as 3D printing, even of metals like titanium, come along, what might be advantages that we could take in terms of reducing our operating empty weight down the road. But for now, we're in many respects a fairly conventional and fairly simple vehicle. So some of the, if you want to call them contrary considerations that we thought about and disregarded for the time being, for example, is variable pitch. We decided that one of the principles of the vehicle that was going to matter most to us from a certifiability standpoint, a manufacturability standpoint, a maintainability standpoint, and affordability standpoint was to keep it simple, absolutely as simple as the vehicle could be. And so it's one of the reasons we have fixed pitch blades on our rotors rather than controllable, pitch rotors. Just as an example, we have very few moving parts on the vehicle. If you count the cooling pumps and the motors and rotors, of course, and I guess you probably want to count the doors, that's pretty much it for moving parts. Fuel cell stacks are pretty simple. It's a box with fabric and gases flowing through it with no moving parts itself. And it's there's no combustion involved, of course. It's a chemical reaction that produces the electricity, the heat, and the water. So I hope that helps. If I missed something, feel free to put it in the chat box and we'll see if I can follow up.
Thank you, Bruce. We're 3 minutes over time, so maybe I'll ask, we have a lot more questions than I think we can answer. I think one question that was sort of unique, I'll try to ask as well. And then probably we'll provide answer to the rest of the questions after the presentation. So one person asked, will aircraft with significant thrust requirements, example, airliner or fighter aircraft, only migrate to sustainable propulsion method once the performance or efficiency gains are large compared to traditional propulsion, or will it be more of a gradual evolution with design changes and compromises where necessary?
Well, just as has always been true in aeronautics and vehicle optimization, it takes a long time. In part because it's hard to pick the winners in all of the technology categories necessary for all the components in the vehicle. You have to put a stake in the ground. Well, all of this technology is moving forward. You have to make a choice. And so the same will be true of hydrogen powertrain systems, that you'll have to put a stake in the ground and then creep along to the next advance. There will very likely be hydrogen systems for at least single aisle transports. You may have seen some of the news out of Airbus, for example, not too many weeks ago about the 3 variants that they're looking at: commuter, a single aisle traditional, and an advanced wing body, integrated blended wing body system, hydrogen based. And so there's a project at the University of Illinois, NASA funded, called CHEETAH. And I don't have my acronym dictionary in front of me, but it's a hydrogen, cryogenic hydrogen powertrain system where they're considering and exploring, researching very low TRL levels, of course, the use of superconducting systems for motors in particular that can help with the and use the temperature of liquid hydrogen as a piece of the solution space, so that you can have large electric motor driven fans that behave like turbines, large turbines, and could be useful on larger commercial transport aircraft. I think this is a case very clearly where and we've seen this before, this event, this happening where using small aircraft as proving grounds for technologies that eventually expand all the way up into the large aircraft is the path to pursue changes that are, you might even say one day, look back and that they look like, in hindsight, they look tectonic, but in foresight, it's hard to say. Thank you.
Awesome. Thank you so much. Maybe this last question we'll ask has very maybe short answer. Does Sky plan to manufacture its own fuel cell stack in-house? If not, who are some of the heavyweights in the aeronautical H2 fuel cell industry?
Well, I can't say, of course, but the companies that are out there, Cummins Hydrogenics, Plug Power, Horizon. There's a company in Europe called Intelligent Energy. There are many of them out. There's one, I'm trying to think of the name of it, that's doing the high temperature work, HyPoint, HYPOINT, HyPoint. Many out there who are plugging away at helping us solve problems in this space, both for terrestrial as well as aeronautical applications.
Awesome. Thank you so much. I know we're 7 minutes over time. There's still a few questions left, but I think at this point we can conclude the presentation and answer the questions afterwards. So with that, I want to thank you, Bruce, for the great presentation, very informative. Some people have asked if it would be possible to provide the presentation afterwards. I'll leave that to you to decide.
Sure.
And yes, so thank you everyone for attending, for asking questions, and please feel free to reach out after the presentation with any further questions or suggestions. Any feedback is highly appreciated. And thank you very much.
Yeah, well, you've been a great audience, as indicated by your questions. It's terrific. Thanks so much. Pleasure to be involved.
Thank you, Bruce. Thanks to all the panelists and all the attendees. You guys have a great rest of the day.